Welcome back, Gen Chem 2. I'm so excited. We're going to start to get a little bit deeper with our laws of thermodynamics. Are you ready? So we're actually going to move past just some thermochemistry and work our way into thermodynamics. So we've actually already tackled the first law of thermodynamics, and that was our last series of videos on our internal energy, our heat flow, and work. Okay, so we've got our heat flow, work, and our internal energy, or that energy of a system. So we're actually going to move into the second and third laws of thermodynamics, and I'm so excited. This is a really fun topic. I'm ready to share it. So our second and third laws, let's start with our second law of thermodynamics. And our second law of thermodynamics is something called entropy. And that is given a capital S, okay? Our term entropy is so fun. It's actually been around for a couple hundred years, this theory of entropy. And I included a bunch of links for just entropy. Of course, our open textbook, and then I've also got a cute little tutorial here that's coming from our textbook, and then again, Wikipedia has some good things. And then our second law of thermodynamics is also on Wikipedia, and I believe the third law of thermodynamics is there also. So what in the world is this term entropy, and how does it have a couple laws of thermodynamics? Well, let's give entropy a deep thought just for a second. I want to ask a question before I actually define entropy. And that question is, okay, hang on a second. What if we have an ice cube and we're going to melt it? Now, from all the videos we've been watching in our Zoom discussions, we know how to do this, right? We're going to add heat. This whole process of melting an ice cube, we know from our last section, would be endothermic. We're going to have to add some kind of heat flow, and we're going to have to put heat in to get that ice cube to melt. So if you set an ice cube out on the counter, it's absorbing that heat from room temperature and it's melting. And you're going from water as a solid to water as a liquid. But hang on a second. Why would that process even happen? Our next couple videos are going to tackle that question. If something's endothermic, we already know that that end process takes energy. We drew that on our diagram. If we're going from our solid to our liquid, boy, we have to actually add heat flow in order to make that happen. But why would that process even happen? It's not going towards something more stable or something more energetically favorable, and you actually have to add heat to make it happen. So have you ever wondered, well, what about these processes that are endothermic? How do they even happen? Well, in our next couple videos, we're going to tackle exactly that question. Why do reactions even happen? How does that work? Well, enthalpy is one of those. That's our first topic, was enthalpy. And we learned that some reactions were endothermic and some were exothermic. Some of them took energy and some of them actually went down in energy or gave us energy, released energy. But now we have a second term, and that we're also going to consider, and that is our entropy. So it is not just heat alone as a factor in our reactions. Entropy is our second law of thermodynamics. It is that the universe tends towards disorder. Okay, I love it. That sounds like the start of every sci-fi movie ever, right? All right, this is actually a law of thermodynamics. What it means is that in our universe, we tend towards randomness. Anything that is more random, anything that lacks order, anything that gives a little bit more freedom. I like to think of this in terms of chemistry as literally freedom. So if you are taking an ice cube and it is a nice packed crystal of water, and you go to a nice puddle of liquid, you're going from a solid to a liquid, you have more freedom, more motion, more disorder, more randomness. You have all of that when you go from a solid to a liquid. You have more freedom to move, more disorder. The actual entropy in the universe will always be moving towards more, will be moving towards positive. You'll always be gaining in entropy. So that is our second law of thermodynamics. So in this process, in fact, our entropy is positive. When we're moving towards more freedom or more disorder, we're going to notice that our entropy is positive. So if you've got this rigid structure, there's not a lot of wiggle room in there, and you move into a puddle of water, and then what could you guess if you move from a puddle of water all the way to steam? Dude, I don't even know how to draw that. Bubbles? Like, so if you then go to steam, even more positive, even more entropy. So this one's a little bit trippy, but it is something that we can calculate. Our entropy is a state function. Okay, it is a state function. It is something that's on our table. It is your S with the little knot. It is on the table. And it is something that we can actually calculate. It is an extrinsic or extensive property. What does that mean? That means that it is actually dependent on things like temperature. So if you want to grab your thermodynamics table, you're going to notice that you have a column that says S. So you have a delta H column, and then you have an S column. So this is our third law of thermodynamics now. Why isn't there a little change symbol in front of our entropy? Well, we are going to calculate entropy, so we will calculate that change in entropy, but on our table, why is it there actually no change there? So it turns out that entropy itself is based on the idea that if you take, and this is our third law of thermodynamics, if you take a completely rigid crystal, I'm just going to draw little molecules in a completely rigid crystal, and you take that crystal to theoretical absolute zero. That's not an okay, that's 0 Kelvin, okay? If you take that all the way to absolute zero, that is 0 Kelvin. And this is a perfect, completely perfect, symmetrical, pure crystal. That this is as rigid of a structure as you can get. And if you take this and you could achieve this perfect crystal at absolute zero, then theoretically your entropy would be 0. Now, do we ever see that in the world that we live in? No. Number one, absolute 0 is theoretical and never been achieved. Although if you ask physicists, I think they would argue that they could probably get there. And then also a completely perfect pure crystal at absolute 0 is not something that just exists on our planet. So this is the only case that you would have your entropy as 0. Everything beyond that has a positive entropy. So if you look at your table and you look at your S's, they will all be positive. You can never really have anything on that table that is S equals 0, because if you look at your table, all of our values are at 298K. We're not at absolute 0, perfect, rigid structures. All right, so what do we even do with this, and how do we care? What do we care? Well, let's take this video to actually calculate S, and then let's take our next video to put it all in perspective, and we're going to tie it back together with enthalpy. So we're going to look at both entropy and enthalpy together. So let's just calculate in this one. How do we calculate with our entropy? How do you know if a reaction is gaining entropy or losing entropy? So let's take our water and let's go back to what we know. Let's use our table. Let's calculate and use both our enthalpy and our entropy. So grab your tables and let's read some values. Okay, I have for hydrogen and oxygen, look at that. In enthalpy, we set those to 0. But now with entropy, they can never be 0. So you can't have a 0 here and here. That even though they're in their elemental form, they have entropy. They have some disorder. They have some freedom. They have some randomness. It can't be 0. We're not at absolute 0. So you can't just guess 0 for that one. You've got to grab your table and read it. Now what I have for hydrogen gas is 130.6. Okay, now check out the units for this one. Entropy is joules over moles Kelvin. All right, first thing to notice is that you're in joules and not kilojoules. And second thing to notice is we are temperature dependent. Okay, but we could guess that. What makes you go from ice to liquid to steam? It's all temperature. And then of course our amounts matter. So in our entropy for hydrogen, we have 130.6. What about our oxygen? I have 205.0. Okay, which one has more freedom? Oxygen. We've got more entropy in oxygen than in hydrogen. I love it. Okay, now let's look at our water. So on our enthalpy, we're going to water liquid. So let's grab our table real quick for that one. In fact, I forgot to write that down. I need to grab my table. So let's look at water liquid for enthalpy. All right, who has that? We've used that a million times over. I have a minus 285.8 kilojoules per mole. Okay, and then now let's look at that enthalpy. Oh, holy crap. It went down 69.91 joules. Okay. All right, remember we're in joules here and kilojoules here. That's going to be a big one. That's the most commonest mistake on our next test. And we're temperature dependent. All right, let me add it into each one of these. All right, so look at that. If we were to guess exothermic or endothermic for this process, right away, I love formation reactions because we don't have to calculate a thing. You've got only zeros there. So are we endothermic or exothermic? We are exothermic. All right, so now let's figure out, are we gaining entropy or are we losing entropy? Are we getting more disordered or moving favorably in the universe if we take our elements and actually make water, or are we doing the opposite and we're actually making something more rigid? So how do you actually compare these numbers? Well, first off, we better balance. You've got moles in here. Okay, so let's take our hydrogen and multiply by 2. And then let's take our water and multiply by 2. And then how do you actually calculate this? Well, our entropy is exactly like enthalpy. Hold your seats. We get to calculate it exactly the same way. We're going to do one major summation. We are going to end up calculating the enthalpy of our reaction. Now it's a change. We're comparing it. And we are also going to take products minus reactants. So it's 2 for the price of 1 on that table, right? We get to use another column in exactly the same way. So let's take our products. And don't forget to multiply by moles. Okay, there's our products minus our reactants. So I've got 130.6 and 205. But we've got moles in there. This one is times 2. All right, so grab your calculator. Let's do this. Let's calculate that change in enthalpy for that reaction. In fact, I have to grab a calculator as well. I did not remember to do this one ahead of time. So let's pause for a second while we take our calculators out. Okay, I have to use my phone, so I'm going to make comments underneath here. All right, and then all right, perfect. So I'm going to write right here just to help you out a little bit. Okay, let's figure out our delta S. All right, minus 466.2. Holy crap. So we have just gone down in entropy. Okay. All right, so let's take a look at what this means and why we give a crap. First of all, we're exact opposite. Our enthalpy and our entropy are opposite. This is a minus. That is not a good thing. Minus means that we are going toward more order. That is opposite of towards, our universe and gaining entropy. We are going down in entropy. That is not a favorable process. But doesn't that make sense? If you look at this side of our reaction, we've got 2 sets of pretty happy, very moving molecules, water and oxygen. They're gases, they're in the gas state. They have an awful lot of freedom, a whole lot of motion there. And then you're actually restricting them by bonding and changing state to liquid. So you have an awful lot more order in your product than you do in your starting material. So we have actually gone down in our entropy for that reaction. Okay, not actually a favorable process. All right, let's do the same thing for another reaction. Okay, let's actually take, and let me rewrite this down just a little bit so we have some space there. Let's try this one more time. I love it because it literally looks really sassy, but it is 2 for the price of 1. We have delta H already down pat, right? And now what we're going to calculate is delta S. So let's do the same thing for both of those. And let's take a second and grab your table. Let's write out some values for each one of those. I'm going to go ahead and write them out. I may just write my units over here to the side, kilojoules per mole. Okay, and then we'll go from there. Elemental chlorine, 0. So what we're looking at is this process of decomposing PCl5. So what do you think, even before we calculate it, if we are going from one substance with 5 bonds and we're breaking into 2 chunks and we're breaking some of those bonds, what does your gut tell you is going to happen with entropy? Are we going to go higher in entropy or lower in entropy? Let's see. Let's go ahead and calculate it. I've got 353. Remember our units out here. We are temperature dependent. Okay. I'm just going to kind of round a little bit. Notice nothing is 0. Remember, it can't be. Everything has some entropy because none of this is a rigid, perfect crystal at 0 Kelvin. So everything has to have, you can't default and put this as 0. Everything has entropy. Everything has some disorder or randomness. So let's go ahead and calculate and see if this reaction is endothermic or exothermic. And the good news is we're already balanced, so that's awesome. So I'm going to go ahead and put my products. So I'm going to put products minus reactants. Okay, and everything was 1 mole. So I'm going to cancel those moles. So I get this overall process actually is endothermic. Okay, totally endothermic. All right, let's try our entropy then. Let's calculate our entropy. And let's do the same thing. Let's take our products. Oops, forgot the L. Okay. All right, there's our products minus our reactants. Okay, I love it. All right, so let's do the math on that. And what do we get? All right, when I plug that in, I get a positive 181.7. All right, did you guess right? Did you get that we were going to gain entropy or go up in entropy? This is very favorable. Okay. Our reaction actually is going towards more randomness or more disorder. That is quite favorable. So that's awesome. So I hope you're getting the picture. We'll do a little bit of this in class on Zoom. But for entropy, we actually can do a nice summation just like our enthalpy. This is something we're going to add to our wheelhouse. We've got 2 factors to consider in thermodynamics, not just one. Enthalpy is our heat flow. Entropy is our universe tending towards disorder. So if you can literally picture a super rigid cube, if you're getting more freedom and more motion and more disorder from that, you are moving positive in entropy, and that is favored in the universe. I love it. So let's take this and stop this video, and we're going to turn right around and do another video on how to put entropy and enthalpy together and have that predict